something extraordinary happened where no one on Earth could watch. A visitor from deep space slipped behind the sun and came back changed. On October 29th, 3i Atlas reached its closest point to the star while our best eyes were blind. When it reappeared, it was brighter than models expected, and its light skewed unnervingly blue. A diffuse halo swelled outward as if lit from within. Yet public tracking streams showed no thrust and no deviation at all. Gravity only. Business as usual. So what in the dark could rewrite the script without nudging the path? Stay with me. Like and subscribe now so you do not miss the next wave of data. Start with the geometry that denied us. For roughly a week, the comet hid in line with the sun from Earth's vantage point, a position that turns most ground-based telescopes into spectators. The moment of closest brush was not a skim over the solar surface, but still close enough to feel punishing radiation. 200 million kilometers is. Not inside the furnace, yet it is a place where fragile bodies often betray their weakness. The narrative many expected was a crack, a crumble, perhaps a fan of debris that marks thermal stress and tidal strain. That is not what we got. Instead of falling apart, 3i Atlas punched through perihelion and emerged with a glow that climbed faster than a simple warm-up would allow. Cameras on solar sentinels registered a coma that stretched hundreds of thousands of kilometers across, like a city of light expanding into a continent. More puzzling than size was color. Reflected sunlight should look like the sun's own spectrum, with a modest tilt toward red or green depending on dust and gas. What we saw leaned blue, which hints at emission rather than reflection, at a light source doing its own work. Here is the twist that tightens the knot. Automatic orbit solutions released to the public showed no course change at all. No tiny shove, no jetting event strong enough to kick the trajectory into a measurable kink. After a week in the dark, the traveller came back to the light, acting as if nothing had happened while looking as if something had definitely happened. That duality is the paradox at the heart of this story. A natural object should either break, dim, or push itself a little off course when activity spikes. This one brightened dramatically and kept flying like a stone. You can hear two voices arguing under that data. One says instrument artifact and selection bias, a temporary configuration that exaggerated color and size. The other says independent platforms agreed, and agreement across platforms is hard to fake. One side reaches for familiar comet behavior and asks for patience. The other points to the timeline that surrounds the blackout and the missing angles many hope to study from Mars and other vantage points. Both voices want the same thing, not drama, but clarity, and clarity demands more than a headline. So, here is the plan for the next 49 minutes. We will step through the full paper trail from the weeks before perihelion to the days after reemergence. We will test the simplest explanations first, and only then entertain bolder ideas if the easy paths fail. We will quantify what brightening actually means rather than hand-waving about it. We will put the blue in context with mechanisms that can really generate energetic light. We will keep score on evidence that supports or undercuts each path, and we will flag what new observations would settle the question. Before that tour, take a breath and scale the stakes. 3i Atlas is not a neighborhood snowball nudged from a local cloud. Age estimates place it older than our sun by billions of years, an endurance record that makes every odd measurement feel like a message from a lost era. If it is natural, it is an ambassador from conditions we no longer see in our own system. If it is not entirely natural, then even the faintest hint of technology drags the Fermi paradox out of the classroom and into the news. The wise move is not to choose a camp to raise the bar. Extraordinary claims must carry extraordinary evidence. Ordinary claims should still carry good evidence. The way to respect both rules is to keep our feet on the ground while we walk the trail of anomalies one by one. The hidden week behind the sun is not a blank, it is a detective gap. Everything that happened before and after is a breadcrumb, and the pattern those crumbs draw across the sky is testable. By the end of this journey, you will have a simple checklist that does not depend on belief. You will know which measurements would favor heating and fluorescence, which would point to internal power, and which would retire the blue entirely as an artifact. You will also know what sky window is opening for amateurs, and what a backyard image can add to the global watch. If the paradox is a mirage, it will dissolve under better light. If the paradox is real, the coming weeks will not hide it. Begin with the part that makes astronomers sit up straight. The working age estimate for 3I Atlas puts it older than our solar system by billions of years. That means this object formed in a very different neighborhood, under very different chemistry and radiation, before the cloud that birthed the sun had even tightened its first spiral. We are not just watching a traveler from another address. We are watching a refugee from another era, a fragment that carries memories of a younger galaxy when giant stars lived fast and died violently, and debris fields were everywhere. Survival over that span of time sounds unreasonable on its face. Comets are often described as dirty snowballs, fragile mixes of ice and dust that crumble when sunlight hits hard or when gravity yanks too close to a big body. Radiation gnaws at surfaces. Micrometeorites chip and pockmark. Spin rates change as vents act like tiny thrusters. Weak objects spin up and fly apart. If that is the rule, how does anything that looks remotely comet-like make it through 10 billion winters and 10 billion summers between the stars? There are ways a body can harden into endurance. Over millions of years, the outer layers can sinter, turning fluffy frost into a crust with strength. Volatiles can retreat inward, leaving a shell that damps the violence of sudden heating. Impacts can weld and compact. If the interior is not a jumble of pebbles but a coherent block of rock and metal with only pockets of trapped gases, the object takes a solar punch without shattering. When 3I Atlas cleared perihelion intact, it sent a simple message. Whatever this is, it is not a flimsy rubble pile. Age also explains why first impressions can mislead. A surface battered for eons will be darkened and rough, more like charcoal than fresh snow. That tends to mute reflection and hide subtle color cues. Yet beneath a weathered rind, there can be reservoirs that still vent when warmed. Ancient does not have to mean inert. The surprise here is not that an old object is active. The surprise is how it is active, with a light curve that ran too fast and a spectrum that leaned blue when it should have leaned red. Think about the timescales in play. The sun has shone for 4.5 billion years. The Earth cooled, crusted, and hosted life within a fraction of that. Civilizations rose and fell in eye blinks by comparison. 3I Atlas may have spent most of its existence drifting in cold darkness, warmed only by occasional brushes with starlight. That kind of life breeds patience. It favors materials that do not fail under long exposure. It favors structures that can take a tidal stretch and a thermal shock and still hold together. The upshot is simple and important. When a very old object behaves in very new ways, the behavior is information. The age pushes us toward models that include more rock, more metal, less water by mass, and pockets of exotic chemistry that turn on only under specific heating profiles. The age also sharpens the narrative tension. If the oddities we are about to examine come from that deep history, then every anomaly is a clue to planetary systems that no longer exist. If the oddities do not fit any natural evolutionary path, then age becomes the most unsettling part of the case. It would mean longevity by design. Hold that fork in the mind while we ground the terms. When we say older than the sun, we are translating a web of clues into a single phrase. Dynamics hint at an interstellar origin rather than a bound orbit. Composition hints at processing paths not common in our backyard. Durability through perihelion hints at cohesion that comets rarely show. None of those alone writes the birth certificate. Together they sketch a lineage that points outward and backward in time. That sketch is enough to justify the rigor we bring to the next questions. What does 10 billion years do to nickel and iron locked in stone? What does it do to carbon dioxide trapped in pores, to trace water, to the crystal structure of grains that have seen cosmic rays for eons? How do those changes affect color when the sun floods the surface, or the pattern of polarization when light scatters off dust? Each of those threads ties directly to measurements already in hand and to new observations queued up for the weeks ahead. The age does not answer those questions, it gives them weight. So the stakes of this section are not only poetic, they are practical. If 3I Atlas is a survivor from a long-extinguished system, then the things it does that look strange by our standards might be normal by its standards. If we can map those standards, we can tell a natural story that makes sense from core to coma. If we cannot, then the chasm between age and behavior widens, and the case for something beyond simple geology grows stronger. Either road is worth walking. Either road leads to discovery. begin with a simple image. You toss a coin and get heads. Toss again and get heads. Keep tossing and the streak grows long enough that you pause. Each flip can be honest, yet a run this long begs a second look. 3i Atlas carries that same energy. One oddity might be a shrug. Two oddities start a conversation. 7 in a row demand an audit. First comes the path. Interstellar visitors should arrive from random angles, yet this one sails almost flat along the same plane, where our planets circle the Sunday. The alignment sits within roughly 5 degrees. Astronomers can put a number to that. It is not impossible, just uncommon enough to raise an eyebrow. In isolation, it proves nothing. In context, it becomes a first heads in a growing streak. Now fold in timing. During its approach, 3i Atlas threaded a schedule that brought it near Mars, Venus, and Jupiter by tens of millions of kilometers and placed it behind the Sun from Earth exactly during closest approach. Again, chance can deal that hand. Space is big, orbits are many, coincidences do happen, yet timing is a storyteller, and this timing whispers that we should keep counting. Then there was the jet that pointed the wrong way. Comet tails usually push away from the Sun because light and solar wind shove dust and gas outward. For weeks in mid-year, this object vented sunward, as if a fire hose were aimed upstream. Multiple instruments from different vantage points confirm the geometry, which rules out a trick of viewing angle. Later, the jet relaxed into a normal away from the sun plume. A brief violation, then a return to the rules. That is not just another heads. It is a coin that flips sideways and then pretends to be ordinary. Composition added weight. Spectra revealed nickel pouring off the object, while iron lagged far behind. In cosmic foundries, iron usually dominates, and nickel rides along as a lesser partner. Here, the partnership seemed inverted. The plume also showed water at around 4% by mass, far lower than the textbook comet where water carries most of the load. A dry traveller that vents metals more easily than many rocks do is an unexpected creature. Polarization pushed the envelope further. When sunlight scatters off dust, the electric field of that light can line up in preferred ways. Plot that alignment, and you get a polarization signature. 3i Atlas landed outside the comfort zone of known comets with a strongly negative signal that resisted easy classification. That kind of result does not mean alien. It does mean welcome to new physics of small particles, or to materials we do not usually grind into comet dust. Stack one more odd card onto the pile with a sky geometry that passes within a handful of degrees of the famous 1977 narrow band. Radio burst, often called the wow signal. No one credible would call that an identification. The sky is large yet crowded, and the old reception region is not a pinprick. Still, direction adds another heads to the run, enough to keep the notebook open. At this point, enthusiastic minds multiply odds and announce an absurdly tiny likelihood that all of this could be natural. That instinct is understandable and also dangerous. Multiplying small chances assumes independence, assumes every number is solid, and assumes no hidden selection effects. Real sky work is messier. Surveys favor certain angles. Humans notice anomalies more than normal behavior. Measurements carry error bars that do not always play nicely together. The honest move is to hold the tiny total with open hands. Use it to justify scrutiny, not to declare victory. The phrase "the odds fight back" means exactly this. Nature is fully capable of dealing you a run that looks rigged. The correct response is not to accuse the dealer. The correct response is to watch more closely, sharpen your tests, and decide which oddities are strong and which melt when you raise the light. Some will fall to better calibration. Some will find a natural home in a model that was too narrow. The stubborn remainder, if any, will deserve bolder hypotheses. There is a human factor to manage along the way. Brains love pattern. We see faces in clouds and meaning in noise. That bias is not a flaw. It is a feature that helped our ancestors survive, and it also fuels discovery when we discipline it. The discipline here is to treat every anomaly as a to-do list item. Verify the angle, recompute the timing, refit the spectra with alternative baselines, check polarization with new filters. Ask whether the materials you think you are seeing could be mimicked by grain size rather than chemistry. If the list shrinks under pressure, the coin streak was luck, and the world still learned something. If the list refuses to shrink, the case grows healthier rather than weaker. Either way, the next step is clear. We must resolve the most dramatic item in the deck, the blue light at perihelion that looks like emission rather than reflection, and that came with brightening far steeper than simple warming can deliver. If that blue survives cross-examination, the narrative cannot stay the same. Begin with the curve that would not behave. As 3I Atlas dropped toward the sun, its brightness did not ramp up like a stove warming a kettle. Observers derived a relationship that rose with the inverse of distance raised to about 7.5. In plain speech, every step closer multiplied the light far faster than simple heating would allow. That is not a gentle slope, that is a wall. Then the halo swelled until it spanned roughly 300,000 kilometers, a luminous cocoon, nearly the distance from Earth to the Moon. Size is striking. Color is the shock. Solar missions with heliospheric imagers and coronagraphs filtered away the glare so the dust and gas around the object could be seen. The light from that envelope leaned blue rather than the softer yellow-white of the solar spectrum. Reflection off dust should echo the Sunday thermal glow from a cool surface should drift redwood, not bluewood. A blue excess points to emission, which means something in or around the body was generating light, not only bouncing it. To lean bluer than the photosphere of the sun, a source must behave as if its color temperature is higher than roughly 5,800 Kelvin. What could do that without shoving the comet off course? Fluorescent gases are the first thought. Solar ultraviolet can pump energy into molecules that then re-emit photons at specific wavelengths, sometimes in the blue-green range. Cyanide compounds are famous for their glow in comets. The catch is scale. Fluorescence tends to write thin lines on a spectrum rather than flood the entire visible output. It produces accent marks, not a dominant chorus. To dominate the color and the brightness at this level, the emitting species would need to be abundant and continuously energized, and the resulting light would still look line-like rather than a broad blue push. Fresh ice is the second thought. If a surface is clean and bright, it can reflect more blue light than a soot-darkened crust. Yet, 3I Atlas is no newborn. An object that has drifted through space for billions of years should wear a weathered rind, irradiated and coated in carbon-rich residue. You can expose new ice if fractures open, but that still leaves a cold mirror. Cold mirrors do not outshine their star in blueness. They simply return what they are given with a modest tilt. Grain-size tricks come next. Very fine dust can scatter light preferentially and change polarization in ways that tilt the apparent color. That is a welcome path to test, since it ties the blue and the odd polarization together. The problem remains magnitude. To drive the brightening wall and the blue shift together, the dust population would need a distribution that both explodes in number and holds an extreme size regime, while the object is being blasted by solar radiation. That is a tall order, not impossible, but tall. If emission is real and strong, the conversation moves to energy. You can imagine shallow chemical sources, perhaps recombination of radicals built up during the cold cruise. You can imagine deeper energy, perhaps decay heat from embedded isotopes that only express themselves when warming unlocks pathways. You can even imagine microarcing in charged dust, a kind of electrical glow in a complex plasma around the nucleus, though that idea must climb a steep hill of skepticism. Each mechanism has signatures we can look for in spectra and in time variability. Emission lines should sharpen, continuum should flatten or steepen in characteristic ways. Pulses should appear or not appear on specific timescales tied to rotation. The other branch of the fork is blunt. The data are wrong. Not fabricated, simply biased by the hard job of extracting faint structure beside a blinding star. Coronagraphs create artificial eclipses. Image. Processing can imprint misleading colors. Calibration files can trail reality by a few days. Independent platforms reduce those risks but do not erase them entirely. When 2 or 3 images agree, confidence rises. When they agree on a feature that fights both reflection and thermal logic, eyes widen, and we ask for a 4th and a 5th look, with different filters and different pipelines. A final wrinkle tightens the plot. The runaway brightening and the blue leaning halo did not come with a measurable kick in the trajectory. If vents were so violent that they lit up space, why did they not act like thrusters and nudge the path? The simplest answer is geometry. gas can roar in many directions that cancel their pushes. The nucleus can tumble in a way that balances torque. A less simple answer is that the light was not tied to high mass flow at all, which brings us back to emission that shines without moving much material. So the perihelion story reads like this. A very old traveller dived through a furnace and came out robed in blue light, wrapped in a halo larger than many planets. The light curve rose too steeply for comfort. The colour leaned the wrong way for reflection and for warmth. The path did not flinch. Either the instruments conspired by accident to write a mirage, or the object lit itself in a way comets rarely do. The next sections will press each explanation until one cracks. Start with the picture frame that is missing its centre. We have gorgeous edges from solar images and coronagraphs. We have pre- and post-scenes from observatories that caught 3i Atlas before it slipped behind the sun and after it stepped back into view. What we do not have are the angles many hoped would tie the whole arc together. The timeline has a clean heartbeat. Early October brought a pass within tens of millions of kilometers of Mars. Late October brought the hidden week behind the Sunday. The very end of October brought reemergence. Between those beats sit doors that did not open. One door is the set of high-resolution frames that the Mars Reconnaissance Orbiter can capture with its powerful camera. If those images exist at the right time, they would bridge the gap between the strange mid-year behavior and the quiet claim of nominal motion. They would show vent geometry, surface texture, maybe even large-scale fractures, or the lack of them. They would also settle a practical question that has haunted this story. Did the object change its behavior near Mars, or did our vantage points change the storytelling while the object kept doing what it always did? Another door leads to ground networks that tracked the approach through late summer. Reports tapered after the Mars encounter from at least one major program that had previously shared frequent updates. The official reasons might be scheduling and priorities. Lunar missions and other projects do consume telescope time, yet the effect is the same for the public and for researchers who work outside those teams. A window closed at the very moment when a change in the plume was later reported by others. You can call that coincidence. You can also call it the kind of coincidence that keeps curiosity awake at night. A third door is the simple promise of bureaucracy to move on time. Spacecraft collect raw pixels. Those pixels move through pipelines with calibration, cleaning, archiving. That takes work and days. When missions queue bursts of observations during a busy season, the queue is long. None of that is sinister. It is how science is done. Still, when an object that already defies easy categories blazes blue at perihelion, and then we learn that the best side angles are weeks or months away, you feel the weight of delay. Discovery is a fire. Delay is rain. Meanwhile, the automated trackers kept publishing tables and plots that said nothing dramatic happened to the orbit. No thrust detected. No course correction. The world looked stable in numbers, while the images that would let us see the texture of that stability were still off stage. That contrast sets up the central question for this part. Are we staring at a normal comet whose odd clothing is a trick of lighting and timing, or are we looking at a rare object that performed its most revealing act during the one interval when our principal eyes were blocked? The only honest answer is to keep two possibilities alive. The gaps can be ordinary. They can be the result of choices, backlogs, and the sheer volume of important things happening across the solar system. Or the gaps can be meaningful. They can hide a transition from a sunward jet to a normal tail that happened in the days around the Mars flyby. They can hide a flare in emission that did not expel enough mass to tip the trajectory, yet did reshape the coma. Until the doors open, the narrative has to carry both tracks and resist the urge to fill silence with invention. There is a way to live productively with that silence. Use it. Sharpen the questions the missing frames must answer. If the Mars camera shows the surface, do we see discrete vents or broad sheets? Do we see bright patches that could expose fresh ice, or dark plates that hint at sintered crust? Do we see boulders and fractures that would betray a rubble interior, or smooth continuity that argues for a monolith? If the plume geometry is clear, does it line up with the later normal tail, or does it show an axis that flipped between the Mars pass and perihelion? The same discipline applies to the ground network that paused its public updates. When that data stream resumes or when parallel campaigns publish, we can test whether the anti-tail truly faded in October and whether the polarization signature evolved with it. If polarization softened toward familiar values at the same time the tail normalized, that ties dust properties to geometry in a satisfying way. If polarization stayed extreme while the tail looked ordinary, that separates the puzzles and forces us to search for deeper causes. All the while, the instruments that did keep watching have their own stories to finish. Solar imagers that first flagged the blue need follow-up sequences with different filters and independent processing teams. Weather satellites with compact coronagraphs should repeat their look to confirm structure in the halo rather than a noise pattern. The point is not to distrust the teams. The point is to let redundancy do its job. When mystery rises, more eyes is not a luxury. It is the method. Silence and gaps are not villains in science. They are invitations to design better tests. The missing frames, the delayed spectra, the paused updates, each will either relax the story back toward a strange but natural comet, or they will harden the case that something unusual happened in the dark. When the doors open, they will not merely add pictures to a gallery. They will answer whether the blue belongs to chemistry and grain size, or whether it belongs to an energy source that comets rarely host. Until then, we prepare the yardsticks and hold the paradox steady. Two stories stand face to face. One says internal power lit the halo without pushing the orbit. The other says unusual but natural chemistry and structure can mimic every surprise. The choice is not belief. The choice is which story makes fewer miracles when tested against the sky. Take the engine idea first. A probe that cruises for ages would treasure energy and would harvest it near stars. A perihelion pass offers a flood of power and a chance to warm systems that slept for eons. Blue-leaning light could be the glow of energetic processes in a sheath close to the surface. The orbit did not flinch, yet a machine could vent in balanced directions or time its activity to cancel torques through rotation. Engines leave fingerprints that exceed poetry. Heat maps would show hotspots that ride with the rotation of the nucleus rather than drift with the sunday. Spectra would show a continuum that stays broad while narrow lines ride on top, a sign that light comes from more than reflected sunlight. The halo would show layers and filaments that repeat with clockwork timing. High-cadence images would reveal periodic pulses that match a stable spin period. There are quieter fingerprints as well. Precision, astrometry across many nights can uncover a tiny residual acceleration that hides below single-frame noise. Radio and microwave surveys can rule in or out narrow band emissions that would be hard to explain with chemistry alone. Co-moving flecks that appear and disappear could be small devices leaving and returning, though that is a steep claim that demands ironclad tracking. Even a null result is information when the boundaries are tight. Now walk the natural road. A planetary fragment can carry metal-rich domains and a skeletal water budget, which fits the low water fraction and the stubborn structural strength. A crust, sintered by ages, can seal pockets of gas that vent along fractures when warmed. Nickel-rich grains can be lofted and then ionized in sunlight, without boiling the metal itself. Ionized carbon dioxide and cyanogen can flood the coma with emission lines that lean blue while dust geometry pushes the color further. The sunward jet that baffled many may not require defiance of physics. Large grains can orbit with the nucleus and form a spike that points sunward when viewed along the orbital plane. That phenomenon has a history in comet studies, a thing seen rarely but not never. As viewing geometry changes through the Mars encounter and the behind-the-sun week, the apparent jet can collapse into a standard tail, even if vent directions on the surface barely change. The switch then belongs to perspective and particle size rather than an onboard decision. Natural models also predict discipline in the numbers. If fluorescence drives much of the blue, spectra should show strong lines that wax and wane with solar, ultraviolet flux, and with the rotation of the nucleus, as vents point in and out of sunlight. If grain size carries the color, polarization should track phase angle in a way that maps onto known scattering laws. If a metal-rich core feeds the coma, mass release rates for nickel should link to dust production and to specific thermal thresholds on approach and departure. Each path comes with risks. The engine story risks the absence of thrust and the absence of engineered symmetry in the halo. The natural story risks the scale of the blue and the steep wall of brightening that simple warming struggles to match. The way through is prediction. Engines forecast phase-locked hotspots, repeatable flares, and perhaps a small but coherent drift in the orbit over many weeks. Ice and rock forecast line-rich spectra, phase-dependent polarization, and a coma structure that evolves smoothly with changing geometry rather than in abrupt jumps. There is a third guide that often clarifies messy debates. Follow the energy. If the light mostly comes from emission, where does the power come from? And how is it moved from source to photons? Decay heat would leave a slow cushion of warmth that does not vanish when the sun slips away. Recombination chemistry would track fresh radicals and would fade quickly when illumination changes. Electrical glow in a dusty plasma would produce sharp time structure and specific spatial morphologies near field lines in the solar wind. Nothing in the sky begs us to choose before the tests run. Engines or ice is a narrative fork, not a verdict. We hold both stories and ask them to compete in daylight. The probe story must live without thrust and prove periodic structure beyond what rotation alone would give a natural vent. The fragment story must shoulder the blue and the brightness wall without borrowing miracles from wishful thinking. Within weeks, the sky will answer with maps, lines, and curves that put one path on life support and give the other new strength. Begin with the most stubborn fact. 3i Atlas did not break. It took the solar punch, then walked away. That single outcome narrows the interior from a loose snow and pebble mix to something that holds together under heating and tidal flex. A monolith is one end of the spectrum, a welded breccia sits near the middle, and a rubble pile is the end we can now discount. Thermal stress at closest approach should have exposed weakness. Instead, the body behaved like a single piece with grip in its grain. Strength is not only an image thing. Thermal inertia leaves a signature in how quickly temperatures swing as sunlight rises and falls over the rotating surface. Stronger, denser interiors conduct heat differently from fluff. Infrared light curves can read that difference like fingerprints. If the skin cools and warms slowly and evenly, you are looking at a cohesive body. If it flickers from patch to patch with wild swings, you are looking at a quilt of disconnected clumps. The perihelion survival already leans to the first case. Follow-up heat maps can close the case. Now put numbers to the plume. Observers estimated a steady nickel release near 4 grams each second across roughly 4 months before perihelion. Multiply 4 grams by about 10 million seconds, and you arrive at roughly 40,000 kilograms. On a nucleus that likely masses tens of billions of kilograms, that mass loss is a whisper. The paradox is not the amount. The paradox is the state. Nickel is not supposed to vaporize at the temperatures a cometary surface reaches, yet nickel species appeared in the coma, where sunlight can ionize them and make them glow. That means the pathway from solid to gas is not simple boiling from a skillet. It is more like tiny grains freed by fracture and abrasion, then lofted and energized by escaping gas, or nickel bound in compounds that release in complex chemistry when warmed. The nickel-to-iron imbalance carries the story. Further, in most cosmic kitchens, iron is the main course, and nickel is garnish. Here the garnish looks oversized, and the main course looks shy. 2 explanations compete on the natural side. 1. The source region is a patch that is nickel-rich by birth, perhaps a metallic vein from deeper inside a parent body that was once differentiated. 2. The iron is present but hides in grains that do not enter the coma as easily, or that fall out of view quickly due to size and charge. Both ideas forecast tests we can run. If a vein feeds the plume, rotation should modulate the nickel signal like a lighthouse. If grain behavior hides iron, polarization and dust size distributions should betray that filter. Add the water budget to the ledger. 4% by mass is a small cup for a comet, and it pairs well with a rocky or metallic interior that stores volatile gases in pockets rather than as a bulk ingredient. A metallic or rock-heavy body can outgas through fractures without shedding much mass. That explains how brightening can race up a wall while the trajectory barely moves. Pressure waves can lift dust and light it, without producing thrust that lasts long enough or aligns cleanly enough to kick the orbit. These pillars converge on a compelling natural frame. Imagine a shard from a once larger world, torn free during a violent encounter long ago. It carries a metal-laced core fragment, a dark crust sintered by time, and sparse volatiles trapped in seams. Warm it, and it breathes in fits and starts. Crack it, and it exhales through specific vents. Stir its skin with sunlight, and you lift grains that scatter light in unusual ways. In that picture, the blue lean and the steep brightening are not miracles. They are the integrated output of composition, structure, and geometry pushed into an extreme regime near the Sunday math gives us clean bets to place. If a metal-rich seam is real, nickel lines should rise and fall on the rotation period and should drift as the subsolar point marches along latitude. If strength is high, the spin period should remain steady within tight bounds rather than wander under jet torques. If the interior conducts well, infrared maps should show smooth day-night gradients rather than patchy thermal islands. If dust is the color driver, polarization should walk a predictable curve with phase angle and should link to a narrow grain size band inferred from scattering. There is room in these bets for a surprise. Should maps reveal hotspots that keep pace with the nucleus rather than with sun angle, or filaments that pulse with a clock that refuses to match rotation, the engine story gathers breath. Should spectra harden into line forests that match known fluorescence, while thermal curves and polarization obey established laws, the fragment story tightens its hold. Either way, strength, metal, and math have moved the conversation from wonder to measurement. The story is now a scorecard, and the sky will decide which column fills first. Circle a date on the mind's calendar. Mid-December brings the best geometry Earth will have for a long while. The comet pulls far enough from the sun's glare for deep integrations while still close enough for rich signal. Telescopes on the ground and in space will finally get the angles that the late October blackout denied. This is not just more pictures. This is a set of decisive tests that can turn mystery into measurement. Spectra come first because light remembers its source. If blue dominance rose from fluorescent gases, December spectra should carve the visible and near ultraviolet into sharp lines that grow or fade with solar ultraviolet flux. If the blue came from a hot continuum source, the spectrum will smooth out into a slope that does not fragment into a forest of narrow features. Rotational phase adds a second lever. If one vent or one seam drives much of the show, line strength should pulse in and out with a steady rhythm tied to spin. If geometry, rather than chemistry, carried the color, line contrasts will weaken, while the broadband scatter shifts with viewing angle. Thermal mapping runs in parallel. Infrared instruments can turn the nucleus into a temperature map that climbs and falls as the sun angle moves. A monolithic interior with good thermal conductivity will show gentle gradients and slow changes. A quilt of weakly bound clumps will show patches that light up and cool down in jerks. The most telling pattern would be hotspots that refuse to follow the Sunday. If regions stay warm as they rotate into night, or flare at the same rotational phase, regardless of illumination, then a buried energy source becomes the simplest reading. Polarization adds the texture of grain size without touching a single grain. As sunlight scatters off dust, the electric field aligns in ways that depend on particle size, porosity, and composition. Measure that alignment across a range of phase angles, and you can back out the dust population. The return from extreme negative values toward familiar curves would argue that earlier extremes were a transient dust regime near perihelion. Persistence of the extreme pattern would keep the door open for unusual materials or charge states in the coma. High-cadence imaging gives the halo a heartbeat. If layers and filaments move with clockwork timing, they will trace the spin and may reveal jets that switch on and off in repeatable arcs. If the structure ripples without rhythm, then the solar wind and local turbulence may be in charge rather than any organized engine. Cadence also catches outbursts that last minutes instead of hours. Short spikes with phase-locked timing would favor a mechanical trigger on the surface. Long drifts that track solar conditions would favor simple heating and chemistry. Precision astrometry is the quiet arbiter. Night after night, many observatories will measure the position against background stars with milliarc-second care. From that slow snowfall of numbers, analysts tease out any non-gravitational acceleration too small for a single frame to show. A steady residual that points away from the sun would be classic outgassing. A residual that hangs with a fixed direction in the nucleus frame would hint at organized activity that does not average away. No residual at all across December would make the engine story stagger, though it would not erase more subtle signatures. Radio and microwave ears will listen, even if silence is likely. Narrowband transmissions are easy to rule out when your receivers sweep cleanly across the dial. Broadband emissions tied to plasma processes are harder, yet characteristic. A null result strengthens the case that the light is chemical and thermal. A faint line that repeats on the rotation period would be a headline, waiting only for confirmation and caution. There is also a geometry puzzle that December can solve. The sunward spike that appeared in mid-year could have been a viewing trick that large. Grains sometimes perform. With the comet now seen from a new angle, that spike should either reappear in a predictable way or vanish cleanly. If it reappears on schedule, the anomaly drops into the box marked rare but known. If it refuses to return while polarization remains strange, the anomaly graduates into a deeper class. None of these tests require belief. They require clear skies, time on instruments, and patient comparison to models that we can state in plain language. Does the spectrum break into lines that track ultraviolet? Do temperatures follow the sunday? Does polarization trace grain size rules? Does the orbit drift? Each question has a yes or a no, or a number on a scale with uncertainty bands that will narrow as data stacks up. The path from wonder to answer is not glamorous, but it is beautiful in its honesty. So December is not just a better look. It is a filter that separates stories. If chemistry and dust geometry own the blue, the measurements will settle into patterns we have seen in other guises. If something inside the traveler is doing work, the maps and curves will refuse to behave like mere reflections of sunlight. The sky will not shout. It will whisper in lines and slopes and tiny shifts. We only have to listen well enough to hear. This is the moment where a global audience becomes a global instrument. 3i Atlas rises before dawn, easing away from the sun's glare night by night, and that creates a window that backyard observers can actually use. You do not need a mountaintop. You need clear horizons, patience, and a plan. Face the low eastern sky in the dark hour before sunrise. Let your eyes settle. Sweep slowly with binoculars if you have them, or a small telescope on a steady mount. The target will not blaze like a planet. Think of a soft glow with a gentle tail, a fragment of fog pinned to the stars. Start simple. If you are imaging, choose short exposures to avoid smearing and take many frames in a row. Later, you can align and stack them so the comet stands still and the noise melts. If you only have a phone and a tripod, try burst mode and keep the lens free of dew. Record what you see even if no camera is involved. A careful sketch with field stars in roughly the right places can be surprisingly useful when the time and direction are accurate. Write down the basics as if you were leaving a breadcrumb trail for another observer to follow. Date and time in universal coordinated time so everyone speaks the same clock. Your location to city level or with latitude and longitude if you can. The direction in the sky and the height above the horizon. The size of your instrument if you used one, or the fact that you observed with unaided eyes. The sky conditions, whether the air was steady or the stars were twinkling hard. These details turn a personal moment into data that professionals can weigh. There are 3 kinds of changes amateurs catch best. First, outbursts. If the coma seems brighter than the night before, or if a small fan appears where there was only a round glow, you may have witnessed a vent waking up. Second, shapeshifts. The tail can kink, split, or grow a spike. A quick sketch with star positions gives analysts a baseline to compare with other locations. Third, timing. If several observers on different continents record the same feature at slightly different times, the rotation period of the nucleus can be pinned down with surprising precision. A word about the glare that haunted perihelion. You are now looking with the sun safely below the horizon, but the low sky still tosses haze and colour at your view. Give yourself margin. Start earlier than you think to set up. Practice on a known cluster or galaxy nearby, so you have the right scale and focus. Then slide to the comet's position with calm hands. If you miss on the first sweep, breathe and start a slow zigzag. Comets reward patience more than aggression. You can also measure without measuring gear. If you can identify a few bright reference stars in the same field, you can estimate brightness by eye. Compare the comet's inner glow to a star you know, then say fainter or brighter by a small step. This is an art, yet when many eyes perform the same art with care, the average settles into truth. Add the colour impression if you can. Do you sense a cold tint in the inner coma, a hint of blue or green? Human colour perception is tricky in low light, but many impressions together can nudge a real signal out of the noise. Citizen recordings matter most when they are shared fast and tagged cleanly. Upload to a trusted network that collects comet observations. Label with the object's name, your time, and your method. Do not chase perfection, chase clarity. If a professional team is on the edge of calling a transient event, your image from an hour earlier can confirm the rise or mark the start. If a rotation period is still fuzzy, your 2 clear nights a week apart can to lock it down. There is a deeper reason to participate. The story of 3i Atlas is not only about data that giant observatories harvest. It is about a world that decides to look up together, to turn curiosity into a shared craft. When a teenager on a balcony in a bright city records the same flare that a veteran observer sees from a rural field, the distance between those lives shrinks. When an image from a village in one hemisphere lines up with an image from the other, the planet behaves like a single wide telescope with mirrors linked by goodwill. Expect nights that yield nothing but cold air and quiet stars. Expect a few where clouds win. Expect one where a faint knot in the coma sharpens and grows while you are watching, and you realize you are the first person on Earth to see that change. That feeling is worth every early alarm. It also builds the archive that will answer our hardest questions. Whether the blue belongs to chemistry or to something else. Whether the strength comes from rock or from design. Whether the tail is a trick of geometry or a signal of hidden heat. The sky will tell us. Thousands of careful eyes will help it speak. Picture 2 doors at the end of a long corridor. Behind one door is a natural world that turns out to be stranger than the guidebook. Behind the other is a whisper of design that refuses to go away. We do not need to force the choice today. We need to understand what each door would mean for the future of looking up. Start with the quiet door. Say, every December test settles into patterns that feel familiar. Lines in the spectrum behave like fluorescing gases. Polarization traces a dust population that drifts back toward known curves. Thermal maps follow the sun with the patience of a stone. The orbit does not show a residual shove beyond what outgassing explains. The blue at perihelion softens into a story about grain size, emission lines, and geometry that conspired for a week to fool our instincts. Nothing magical, only physics doing what physics does when an ancient object is pushed into a brutal regime. That ending is not a defeat. It is a new chapter in a book we thought we had finished. A fragment from a forgotten system would teach us that comet families are broader than we assumed. It would give us a template for metal-rich shards with thin water budgets and durable interiors. It would expand the playbook for jets that look sunward when seen edge-on, for polarization states that go negative when grains cross a tight-sized band, and for light curves that can rise like a wall without tearing an object apart. It would refine how we search, what we expect, and how we avoid fooling ourselves the next time a visitor streaks past. It would also move a weight from the chest. When a mystery yields to patient measurement, the world breathes easier and stands taller. Students learn that wonder is not an enemy of rigor. Amateurs learn that careful notes matter. Professionals learn, again, that the first explanation is rarely the last, and that discipline is a kind of love. The night sky does not shrink, it grows. We add a page about planetary fragments and sintered crusts and nickel-rich plumes to the atlas of what is possible. Now open the second door a crack. Say 1 or 2 tests refuse to play along. Hotspots that hold warmth through night in the nucleus frame. Filaments that pulse with a clock that will not align with solar angle or with rotation plus vents. A tiny residual in the orbit that points with a fixed direction rather than away from the Sunday. A narrow radio line that whispers every few hours and then fades. Nothing loud, nothing cinematic. Just a handful of clues that survive every attempt to erase them and that sketch the outline of purpose in a place where geology alone struggles. That ending would not give us a greeting. It would not hand us coordinates or a manifesto. It would give us something both smaller and larger. Smaller, because confirmation would take months and years of grimy work. Larger, because even a single credible hint that technology can last across starflight and deep time would transform the frame in which we think. The question would stop being whether minds have walked this road before and become how often, how far, and how quietly. Funding priorities would tilt toward interception missions. Search strategies would broaden to include patient hunts for artifacts that mimic nature on purpose. Philosophy would bend, so would art, so would the way a child looks up. Either door changes the world in honest ways. If nothing changes in the sense that every anomaly relaxes into physics, we still gain a durable lesson about humility and craft. If something refuses to relax, we gain a new horizon and a set of responsibilities that come with it. In both futures, the same tools carry us forward: better surveys that net more interstellar objects, faster pipelines that share data without smearing it, open collaborations that survive politics and pride, classrooms that teach skepticism and wonder as a pair rather than as rivals. There is one more truth that belongs at the end of this road. The sky rarely answers in a shout. It answers in number columns that creep, in lines that sharpen, in images that look ordinary until you stack 100 of them and the pattern rises. The work is not a spectacle. It is a practice. You set the scope, you run the code, you compare the shapes, you sleep, you rise, you try again. A week becomes a season becomes a year. Then one morning the corridor ends, the door swings, and the room beyond is not what you expected, but it is better. It is the kind of room you can live in.